What's up? Welcome to Chemistry 101 with me, your host, Brian Tran, accompanied by my lovely assistants,
Dom.
Kaizen.
And Michelle.
Today we'll be touching on the topic of Graham's Law and Avogadro's Law. No, not Graham's Law, Avocado's Law. We're talking about Thomas Graham and Amadeo Avogadro.
So first off, we're going to explain a law. First off, what is a law? In basic terms, it's a rule or regulation that must be followed when doing something. We have laws for driving, laws for math, laws for our government, and here laws for chemistry.
Alright, so who is this Graham dude and what is his law? Well, let's start with some background info. So Graham was a Scottish chemist living in the 1800s who developed the method of gas diffusion. Graham's first important paper dealt with the diffusion of gases in 1829. He developed Graham's law or diffusion of rate of gases and also found that the relative rate of the effusion of gases are comparable to the diffusion rates. From examining the diffusion of one liquid into another, he divided particles into two classes: crystalloids, such as common salts, having high diffusibility, and colloids, such as gum arabic, having low diffusibility. He devised dialysis, a method for separating colloids from crystalloids, and also proved that the process of liquid diffusion causes partial decomposition of certain chemical compounds.
Now, Graham's law expresses the relationship between effusion and diffusion. The law directly relates to the diffusion and effusion of molecules to the speed of which the molecules move. Density affects the speed of which molecules move. Gaseous particles are in constant random motion. Gaseous particles tend to undergo diffusion because they have kinetic energy. Diffusion is faster at higher temperatures because the gas molecules have greater kinetic energy. Diffusion refers to the movement of gas particles through a small hole.
Alright, now what y'all see here is a formula for effusion. Graham's law states that the rate of effusion of gases is inversely proportional to the square root of the density of the gas. The rate of effusion can be found using the formula R equals V over T, where R represents rate, V for the volume of the chemical or substance, and T is time. Now let's do some demonstrations of this law. What is the rate of effusion for a gas that has a molar mass twice that of a gas that effuses at a rate of 4.2 moles per minute? The answer is 3.0 moles per minute.
Here's another problem example for the rate of diffusion. How much faster does nitrogen gas diffuse from oxygen gas? Now, to solve this problem, you must first know the formula for the rate of equation. Let's say that you chose nitrogen as gas A and oxygen as gas B. The rate of the oxygen gas divided to the rate of the nitrogen is equal to the square root of the molar mass of the oxygen divided to the molar mass of nitrogen gas. The answer that you will get to this problem is 1.07 per gas. It would be helpful if you put over 1 to it to indicate that for every 1.07 mole of nitrogen gas that diffused, 1.00 mole of oxygen gas.
And now we move
diffused.
on to Avogadro's law. No, not avocado. Thought we already discussed about this. Now this is not about the 6.02 times 10 to the power 23rd. This is the Avogadro's law. Now Avogadro's law states that all gases show the same physical behavior. Additionally, gases with a larger volume must consist of a greater number of particles. It also states that equal volumes of gases at the same temperature and pressure contains an equal numbers of particles.
Avogadro is chiefly remembered for his molecular hypothesis in which he claimed that equal volumes of all gases at the same temperature and pressure contain the same number of molecules. He used this hypothesis further by assuming that the fundamental units of elementary gases may actually divide during chemical reactions. It also allowed for the calculation of molecular weights of gases relatively to some chosen standard. Avogadro typically used the density of hydrogen gas as the standard for comparison, so the formula is V1 over N1 equals V2 over N2.
So let's take this into an example. A 6.0 liter sample at 2.025 degrees Celsius and 2.00 at the atmosphere pressure and contains about half a mole of a gas. If an additional 0.25 mole of gas at the same pressure and temperature are added, what is the final total of the volume of the gas? Our solution is we first express out the Avogadro law by its formula. V1 divided by N1 is equal to V2 divided by N2, where V1 is the initial value, N1 is the initial number of moles, V2 is the final value, and N2 is the final number of moles. Where V1 is 6.0 liters, N1 is 0.5 of a mole, and where 0.25 mole is added, N2 is equal to N1 plus 0.25, NF is equal to 0.75 mole. The one only variable missing is the final value V1. So our goal is to basically solve for VF. So VF will equal to VI times NF divided by NI. Simplify all of that, you get NF is equal to 6.0 liters times 0.75 moles divided by 0.5 moles. And that all of that is equal to 4.5 liters divided by 0.5 VF is equal to 9 liters.
So here's another example. A cylinder with a moving piston contains 2.00 grams of helium at room temperature. More helium was added to the cylinder and the volume was adjusted so that the gas pressure remained the same. How many grams of helium was added to the cylinder if 5 liters, constant temperature? So the solution would be first the formula V1 over N1 equals V2 over N2, and then we change the grams into moles with 2.00 grams over 4.00 moles to 0.50 moles. Then we use Avogadro's law and divide 2.00 liters by 0.500 moles, equaling to 2.50 liters over x. Continuing to simplify, then it would equal x equals 0.625 moles, which is not the final answer. So then for step 4, we take the convert it back to grams, multiplying 4.00 grams per mole by 0.125, which equals 0.500 grams
And so
per
this
mole.
concludes our lesson on Graham's law and Avogadro's law. Thank you for joining us on Chemistry 101. See you next time.